Hi, everyone, and welcome back. We are going to continue our discussion and conversation around silent data corruption, and now we'll focus a little bit more on the solution space. So, again, with me are Rama, Amar, and Rob. And continuing our discussion here, we're going to talk a little bit about who's the advocate for existing and potential solutions. Are you going to make chip vendors implement these on their chips? Are you doing anything differently on your own chips, like the hyperscaler companies?
And Jodaka, before we start, I gotta say, I feel a little bit uncomfortable right now being sandwiched between my two customers. I don't know if that's intentional.
Not intentional, but well, I'm sure they'll be nice to you.
Yes, please be nice. Please be nice.
But yeah, whoever would like to kick it off?
Yeah, I think the solutions lie, up and down the stack, right? Obviously, the chip vendors have to do better architecturally and in the DFT methods and better detection methods. The challenge is that there's also degradation and aging issue. So that forces a sort of in situ screening model that also has to be there. So the workloads have to become resilient to these, because even let's say you screen these and before they come to the data center, they are all clean and you're confident they're not defective. The degradation and aging issue forces you to also have an in situ screening method. So building resiliency in our software systems and critical services and better screening methods and being able to sweep the fleet while it's executing production workloads is going to be a continued requirement. So I don't think there is a solution that's restricted to just the chips or the software vendors or the data center providers and cloud service providers. I think you need the solution to span all of them. Not all software can be made resilient. If the chip is made more resilient, it helps all software. But because of degradation and aging, there's no choice but to also have an in situ screening method and more resilient software to be built here.
Yeah, I totally agree. It's a fallacy to think that this is a chip design or manufacturing problem alone. Most of us in this space are familiar with the bathtub curve. At the beginning of life, usually in the first 6 months to a year, you have the front edge of that. You get early life failures or infant mortalities. And then as the part ages, then at the end of its life, you start having aging effects. So there is no solution of just like pushing this back upstream to the chip vendors and say, no, give us perfect chips. Even if they give us perfect chips at T equals 0, we still are going to have to deal with this problem in the data center.
You're off the hook on
Yeah, no, exactly. Thank you for that.
No, he's on the hook for perfect screening.
I'm
That's what
glad
I just said, right?
we talked about
No
this.
pressure.
But yeah, it is a cross-layer solution, right?
Yeah.
You can't pass on the cost to just one layer, because that's just intractable. So obviously we have to do what we can at the chip level, but there's some cost, to everything that we do. So all the additional screening that we add at ATE or SLT can be very costly. As we mentioned, power efficiency can take a hit, if we overdo it in terms of guard banding. And so we have to work, I think, cross-layer, our vendors here to see, well, what can we do at the chip level to kind of limit exposure at the system level, and then work with them and what additional needs to be done at the system level, hardware, at the system level, software.
Yeah.
Maybe that will provide a more optimal solution than just having, everything being done at one layer.
Yeah, I fully agree with that.
Whenever the issue of cost comes up, obviously my red flags all start to go up here, right?
Yeah.
Because I think there has to be an incentive structure for the chip vendors and the manufacturers to do better. The current incentive structure isn't aligned with that, right? We send them a defective part, they send us a replacement. That's practically no cost to them, right? Now, let's say the incentive was that, look, for each defective chip that we can show and verify that it's indeed defective, you give us 50 times the cost back. Suddenly, the equation will change. The vendors and manufacturers will start to do much better. I think the current model, of incentive structure is not right. And this claims that, 500 DPPM is what we promise. That's a joke, right? That's just not stood the test of time, right? And the data shows that the defect rates are far higher. But the incentive structure has to be such that the vendors and the manufacturers also feel the pain, right? And perhaps this kind of a method by where if the customer sort of brings up a defective part and can verify that, look, here is where it's sort of not behaving as per spec, the cost to you is huge, then behavior will change. Right now, I don't believe that the incentive structure of the vendors not meeting their DPPM goals or, just sending us the replacement part, which might also be defective, is not working. I think this model, this handshake of the contract is, I think, obsolete and needs to be revisited.
So I'll talk about the other end of the pipeline, which is future products and future features. And your question was something about who's going to I can't remember the exact wording, but who's going to advocate for the features? And it's not really easy for us as customers to prescribe a solution, because even within the chip design space, you've got architecture, you've got design, you've got manufacturing, you've got post silicon screening, in-field testing, like all these features that span their whole stack. And so it's hard for us to prescribe what a solution is. Like, we can talk about a DPM goal, or we can talk about a fit rate, but it's hard to prescribe features. But on the other hand, we want to see those features in there. Like, we want some kind of, I call this feature assurance. Like, we want to know that they're taking the problem seriously and they're putting in features. And to use an analogy I like to use, you would never buy a car that didn't have any sensors in it. Like, you couldn't tell what the coolant temperature was or the oil pressure. Like, that would just be crazy. Even though the car is no more likely to fail than it is with those, you want those to feel like, I'm going to know if something is wrong. It's kind of the same thing. So, I want to see all of the features, because if you screw up and you don't meet those targets that we're setting, we don't find out about it until like a year or 2 years after launch, where we have volume and now we're seeing big problems, and it's kind of too late to do anything at that point.
Now, I'll draw kind of an analogy to the functional safety domain. Having worked on safety critical systems in automotive and avionics previously, I think what works well there is the compliance to the governing standards, which say, here's the metrics that you need to meet to be at a certain safety integrity level, or let's say ASIL D or design assurance level A for avionics. Do you think something like that would be helpful, for RAS, to address SDC? And, what's happening there in terms of the standardization space to drive that?
I think so, some kind of standardization of expectations is a good thing. And again, that's one of the things that I think we're going to address in our OCP workstream. But the kinds of solutions that get used in that space, maybe some of those translate over. Rama gave an example earlier of temporary lockstep. Like, maybe there's some opportunity there. But to expect that kind of redundancy at the cloud scale is just not practical. We can't triple the size of the cloud in order to make it redundant. That's just bonkers. We can't even get enough capacity and power as it is. So how are we going to adopt that solution? Now, you can adopt it at the application level for particular solutions, but what we're talking about here is more like raising the bar, like the status quo for the vast majority of computation that's not going to have a specialized resilience solution. And that's what we need to address, and that makes everything better.
Yeah. One of the things I'd like to remind, my two panelists here, Rob and Rama, they have their own custom silicon teams that are actually building the silicon for data centers. So all these requests that are being pushed to us are actually being pushed to their own people.
It's just reflecting them back.
Yeah, but they're very valid. They're very, very valid, right? We need to have silicon that's got, as Rob said, the telemetry in place to be able to mitigate against SDC. That is something that we take really seriously, at least for our own physical designs that we're doing internally. I can tell you that SDC is very heavily talked about, within ARM. Our SVPs, know the term very well. It's definitely not something that's just, a low-level activity. It's a very high-level activity. We are talking about what can we do at AT and SLT to improve, screening. That was mentioned. So again, just like the custom silicon teams at Microsoft and Google would have to take that into account. We also would have to take that into account for our own customers, that would use our own physical design. In ATE, we've been talking about structural testing and DFT, but there's also what we call functional testing at ATE that we're trying to put a lot of effort. Potentially using some of the functional verification tests that we have that we use for architecture, how we can leverage those for better screening capability at the ATE and post silicon. So we are, this is something that is definitely being taken very, very seriously. At the SLT, we're willing to spend a lot of test time at SLT to try and screen out these defects. But then again, there's like some level, at which it becomes prohibitively too expensive to do, and that's why we think that the ultimate solution will be to work with our partners to figure out how much can we do upstream versus how much they can do downstream.
Yeah.
All of that's great, but also remember what we talked about earlier. The problem doesn't end at the point where it gets into our data center. The problem goes on for the lifetime of the part, so we need the features to handle the part in operation. And that means making those trade-offs and saying, okay, I'm going to commit to something like residue computation, or I'm going to commit to using a more advanced ECC scheme, even though it's going to have cost. But that's what it's going to take to address it.
That's a great segue into the next topic, because I was going to talk about silicon lifecycle management, which is what I work on in my day job, focusing on monitoring, data collection, and analytics, at all phases of development, right? All the way from design to manufacturing, yield, in-field. And so, when we talk about silent data corruption, what is that scope? Is that covering time zero as well as the in-field, like the predictive maintenance that Amar was referring to? And, how would you consider it? What is the scope that you would consider?
I gave a little bit of a taxonomy earlier of like we have the time equals zero detectable defects, and that you can address through the kinds of things that Amar was just talking about.
Yeah.
After that, you've got the early life failures. You have still some failures that happen in mature life, and then you have the end of life effects. So we kind of think of them, at least that's the way that I think of them.
Yeah.
And you may do something differently when you're managing the life cycle in the data center. For example, you're doing additional screening and basically expecting more failures at the ends of the bathtub curve, whereas in the middle, maybe you can, if the data is supporting it, you can use a more, conservative regimen. So I guess that's the way I think of it.
Yeah, I think there's no, easy answer. But what is clear is we need periodic screening because of these degradation and aging issues. And we don't have enough data to say, okay, should the model expect the bathtub kind of behavior? The other challenge is that we see other kinds of failures also sort of coming into the space, which makes it very hard to distill, which is SDC, which is other kind of issues. So looking at these things holistically is important. And, my view is that, cost is something engineers are very good at figuring out how to reduce. But I think first we need a solution. I think we are at the point where we constantly say cost is prohibitive and don't even attempt the solution. Right? The yield curve will be thrown, or this cost issue, PPA, all that. My view is that, we have to take a bold step and say, okay, yeah, this will be expensive, but let's sort of invest in this, and then let's figure out how we make the cost more practical. And in many creative ways, dynamic lockstep is one. Residue arithmetic and sort of modulo what arithmetic you want to do. Is it 4-bit, 7-bit? There are many sort of ways to figure out how to scale up and down the cost. Right? If I suspect something has gone wrong, maybe I do a heavy duty enablement of these features.
Yeah.
Right? If I don't suspect and things are going smoothly, I reduce it. Right? If it's sort of coming to the point that I want to do a periodic screen, I can scale it up. So modes of operation are possible where you can sort of fine-tune what the cost level you're going to tolerate based on the kind of problem you're facing. But that option should exist. The problem is without a solution in sight, the cost becomes a, sort of an academic exercise, right? Someone has to actually first implement these things, right?
Yes.
Implement full residue for integer and floating point, protect all data paths, protect all memories. Every area of the chip has some protection, right? Enable lockstep, enable dynamic lockstep, saying, okay, I want dynamic lockstep only on this core. There are so many ways in which you can modulate the cost to manage what you're trying to do. But my worry is that the cost is one that brings up roadblocks to even starting on the solution. Right? I think once we have the solution, there are many creative engineers who figure out how to make the cost more digestible. Right?
It's a great point. I think I fully agree with you that this needs to be addressed. We need to take on that burden. The question is who takes it on and who in the value chain should pay for it, right? So some of the mitigations you mentioned were the hardware mitigations, but they can also be mitigations in software and the application layer, for example. So who should take on that?
Right now, we are paying the cost.
Yeah.
Right, so it's not like nobody's paying the cost.
Right.
I think everyone has a role to play. The chip vendors, the tool vendors have to get far better at providing the tools to be able to find these things or improve our methodology. I think the telemetry that has to go in the DFT methods, the software. I think everyone has to share in this cost. And my worry is, that the architects and those that are worried about PPA, and they should be, PPA is super important, are probably not exploring some of the options that could be made practical, that may initially seem impractical. But first, let's get a solution.
We need to turn it into PPAR.
Yes,
where the R is
reliability,
resilient.
yes.
PPAC.
Right?
Yeah, and actually,
Yeah.
on the comment about telemetry, right, since you brought up silicon lifecycle management,
Right.
that is actually a very smart way of being able to still be power efficient, yet catch a lot of the SDCs. The one thing, though, that I want to, bring up to my panelists here, from Google and Microsoft, is that the way telemetry can work in order to help or silicon, lifecycle management tools, is that by the vendors being very open about the data that's being collected out of those sensors. And this is one challenge that we're facing. When we talk to our vendors, whether it's Google or Microsoft, is the ability to share that data, because you have to train the sensors.
Yeah.
Because you won't be able to figure out like the correlation between SDC and sensor data, from the get-go. There's going to be some sort of training and data collection, that enables you to make that correlation. So that's also another thing that needs to be discussed. How can we openly share data with each other?
Yeah. It's a great question. Yeah, it's a great
Yeah.
point, and it's a challenge today. So thoughts on that from you guys?
Yeah, I think OCP, I think Rob brought this up. OCP has this charter to make, suspect machines or known confirmed SDC chips and machines available to the community, academic community, for them to do research on. And whatever data is relevant to advance the state of the research, we will contribute. I think Intel has done a great job by putting out open DC diags, making some of the machines available to the academic community. Google has done the same. And I think more of this has to happen to create a collection of these data sets and suspect machines. Let's convert some of these defective parts into high value parts for research, right? And make them available to the community. That is the charter of OCP. That's precisely what this OCP, SDC, and reliability panel is working on, right?
Yeah.
So that is a common venue where everyone contributes towards a solution that benefits the entire industry, right?
Yeah.
And so Google has made this commitment, and we had this discussion actually with the NSF director, Margaret, when she brought this up, saying that, look, this is how we can partner, but you need to fund this area of research.
Yeah.
This is an area that requires fundamental research. Here are the kinds of tools we'll make available, some of these defective parts, the data sets that go with it, the logs that show why this is a confirmed detection. So researchers can figure out how to make this detection faster, or what architectural hooks need to be added to find these more easily, or eliminate these, what kind of telemetry needs to go. All that will come. I mean, I think no one is against sharing data that will advance the state of the art here.
Right.
Right? As long as it doesn't violate some PII information or what have you.
This is
I think
great.
This is
great.
something that we have committed through OCP and also
And I
with
think,
the NSF.
but I think beyond open OCP, there's some data between vendor and customer. So for example, we have our sensors on the chip collecting all that data, right? It's being logged, while it's being used in the data center, right? It's being logged to a customer's cloud.
Yeah.
But we need that data that's being logged to be downloaded back to us so that we can make those correlations between SDC events and sensor data.
And with all our vendors, anything that helps in debugging or root causing these, we have shared, as long as it doesn't violate any PI information or any leak of proprietary information. We have always shared the logs, the screens, and stuff like that. So I don't think this is a new request or a request where progress is being held back because of lack of sharing.
Actually, I often give the guidance that I'm afraid that chip designers are going to build what they think is a great sensor and probably fits well into all of their models, and then we've seen when you get things at scale, they don't always match what the models indicate, and so I encourage strongly, make it tunable, make it so that we can share data with you and you can refine that.
That's
correct.
Whatever you're measuring,
I think, yeah.
So we can train our sensors, right?
On this point, I mean, our experience is that, oftentimes when vendors are not able to root cause, they'll say it's a marginality issue. It's actually a sort of a euphemism for we don't know what is going on, right? Because when we do our testing and we sort of screen at, different voltage, frequency, temperature, and what have you, we do not see any evidence that, those are primarily the issues. Occasionally what we see is, let's say at low voltage, we can reproduce the failure faster, but not that it finds new failures, right? So it's that evidence is still not, I would say, engineering backed at this time, right? So while we need to explore because we do not know, we don't have enough data samples, I think we need to think more holistically and see, hey, what is it that we are seeing?
And sensors will help address this, right? Because we're going to be measure voltage, we're going to measure temperature, we're going to measure process skew, we're going to measure droop events if they happen, aging. So the sensor data is going to collect all the information about what's going on when the chip fails,
Right.
or when it doesn't, right? So that we can correlate and make that correlation. But that requires that requires me to download all that data back, even from the parts that didn't fail, because I need to find out, if there's a correlation between sensor readings and parts that don't fail versus parts that fail.
Right, exactly.
So that's the data that I'm talking about that needs to be shared.
I think we have never said no to sharing information that will help make systems better, right? Caveat, the restrictions that Google has on proprietary personal PI information and other restrictions. If it's just logs that you want of the systems that can be sanitized and shared, I don't see any challenges there.
I think when you mentioned the circuit marginalities as well, the approach in the industry also with SLM, with the Silicon Lifecycle Management is, we have these monitors and sensors on the chip, there are eyes on the chip, and we're looking at outliers, right? So we're looking at detecting those outliers and taking the corrective action as needed. How do we determine that? We are looking at the Pareto of the different fault types, technology node by technology node, and looking at that, looking at how those faults would manifest in the field, what are the symptoms that they would exhibit, and then designing our sensors and monitors to look for those signatures, whether it's timing delays or leakages, how those manifest, and then using those to detect the outliers, and then that feedback loop needs to happen, as you mentioned, right? So, and we need to use that data to optimize our models and, use the measurements to be able to do that revision. So I think that's currently the approach, at least for the in-field part, because we also see, there could be some escapes in the field there, like walking wounded parts, or they could be defects that are not present at time zero, but they start to grow and get symptomatic in the field. So those, that's where the SLM solution is being used to detect those and take corrective action as needed to extend the life of the part, so that we can address SDC. So thoughts about that, or any other suggestions from your side?
Yeah, I'm not sure. I mean, I think we should try everything. Is my view.
Yeah.
Right. It's not like we have figured it out and this is the best and right approach. So my view is we are at that stage where all ideas should be fully explored, and the promising ones will emerge that we sort of all align towards and then adopt. Right. Certainly telemetry and sensors and margins all are active areas of research. And then depending on what we learn, we'll have to figure out how to adapt. I don't think we should be wedded to one option saying this is the right solution because no one has this figured out.
Right.
And so when you're in this phase, you should sort of explore as many options as possible and see which ones are the most promising.
Yeah. No, I fully agree. And I also wanted to mention that I think, we talked about the whole community coming together, and I think one way to do that is through the standardization initiatives. You mentioned OCP. There's also some work happening in IEEE, also some in ISO. So, for example, IEEE, the 1856 standard on prognostics, where they talk about the fault life cycle, the metrics. IEEE, there's a P2851 working group that I drive on standardization. And then there's the ISO 26262 third edition that is going to include, the TR 9839 report on prognostics as well. So getting engaged in the standardization initiatives, together with all of the stakeholders across the value chain, and discussing this problem together and addressing the solution.
I think that certainly has merit. My past experience with standardization, unfortunately, taints some of my thinking here. These things take forever and tend to settle on the lowest common denominator. I just worry about that happening in this kind of space also, right? I think at least understanding the terminology, the measurement methods, and being consistent there, so everyone has a deeper understanding of the problem and the scope of the problem, is certainly very useful. We need to worry a little bit about the time it takes for standardization, and how it always sort of settles on the lowest common denominator is something we have to actively fight.
It's a great point, for sure. I think that has to be fast-paced, and we have to solve the problem in a reasonable time so it's still relevant.
Yes.
Even in the OCP space, if you look at what we're specifying and standardizing, it's kind of how do we communicate and how do we work together. It's not what the solutions are.
Right.
It's how do we make progress and be able to share results and reproduce results and like have a
kind of the framework for how to
the
share
framework,
data.
right?
Yeah.
The framework and tools like that. That's kind of in metrics also. That's kind of where the action is, so that we can enable that exploration to find the best solutions.
Great discussion, and I think at this point we'll turn it over to each of you for any concluding remarks you have on this topic and on also the previous panel that we had. So I'll start with you, Rama.
Yeah, I believe this is a really hard problem that merits all hands on deck approach, right? I think the goal of this panel also is to motivate everyone to get engaged, especially the academic community, to come up with creative ideas for the vendors and the manufacturers to figure out what they can do better, for the hyperscaler providers to become enablers in the end-to-end solutions and enable the community to have access to the kinds of systems that are needed or the logs for them to make progress. I think this is an industry-wide problem. It needs an industry-wide approach to solving it, and I hope everyone gets engaged.
Thanks, Rama.
Yes, absolutely. This is a cross-layer effort. Everybody needs to be engaged. As Rob mentioned, we have Open Compute that will give us the framework for how we can share data, because that's going to be very important between the system and the chip level guys to be sharing that data, so that we can come at a reasonable solution, that addresses the problem while still, keeping our designs, competitive.
Great. Well, I don't have a ton to add on top of what these guys have already said, but maybe the whole panel is gone and we haven't talked about AI, so maybe I should do that. This is actually an interesting opportunity to use AI or machine learning to help us diagnose problematic parts. One of the challenges, like we knew periodic screening, but periodic screening isn't 100%, right? We're only as good as the tools. And even if I have a reproduction on something, I could take the same test and run it 10 times, and 5 of them pass and 5 of them fail. Like, it's not as deterministic as you might think, because the faults are not like basic stuck-out kinds of faults. They're, require the moons to align in the right conditions. So you can still miss parts, and we end up with systems that we don't have a screen that catches it, but we know something's wrong with it, like a lemon. But there are some symptoms that we get as infrastructure providers, and if you can build a correlation between those symptoms, it's not going to tell you very definitively, like, this part is bad. But what it can tell you is that you have an elevated probability of failure, and so then you can start taking corrective action. You can increase the screening frequency, longer duration. You can use Rama's dynamic loft step. You can do something to treat that part a little bit differently based on the predicted model. And I think that's a pretty interesting space to explore, but it requires kind of more data on which to do all the training. And we have tons and tons of data. So at least so far, I feel like some curation is needed, because the signal is so light that you have to really be intentional about what you're trying to train on. But I think that's an interesting angle, and maybe there's an opportunity for collaboration there.
Great. Yeah, no, all very great points. Thank you for that. My view is that, innovation always happens at the intersection of technologies. And so, we look for opportunities to innovate, in this case, under that dependability umbrella, between the intersection of reliability and functional safety, between reliability and cybersecurity, or other, related technologies, and see how we can leverage best known methods from those, domains for, to solve our SDC problems. So this was going to be an ongoing discussion, and, we're going to continue the panel series, but thank you again to all of you, for all the panelists, for joining us, and thanks everyone as well for attending and joining, and we'll see you again soon. Stay tuned. Bye.
Thank you.
Thanks much, Jyotika.
Thank you, Jyotika.
Thank you.